Okay, hi folks. Let's get into this learning goal 4. Know how to solve second order differential equations via the Ansatz method. This isn't something that's in the textbook. So typically a lot of PCHEM classes or PCHEM departments might require you to take differential equations as a prereq. We're just going to be learning how to do the necessary differential equations as we go. So I've got this supplemental math document that's also posted on the Canvas site that we're going to use as a guide. So let's get into it. So let's see here, find the slide. Okay, so the Ansatz method literally means guess. So Ansatz is German for guess, okay? The Deutsche for guess the solution. And when we have differential equations in some kind of standard form, there are standard guesses we can make. So for example, this is our standard second order differential equation that I like to call diffie Q. So this is the standard form, and then now with this whole thing set equal to 0, this is what we call the reduced form. And when we get our second order differential equation into this standard reduced form, we can make the following guess. We're going to guess that y equals e to the mx, where m is some constant, and we're also going to impose that that cannot be equal to 0. Because if we just said call y equal to 0, then it'd be way too easy to solve, and we wouldn't have an appropriate wave function anyways. So now what we're going to do is take the first derivative and second derivative of our guess. So recall, when I take the derivative of this exponential function, we take the derivative of what's inside the exponent, and that comes down in front, me to the mx. And then we will take the second derivative of that, and that becomes m squared e to the mx, okay? And so now what we can do is plug these things back into our reduced form, and we'll see that it's going to make solving this equation for y much easier. So I'll just remind you, right? We're solving for y. Okay, so when we plug this in here, this becomes m squared e mx plus, and we're going to keep that constant a there, and now multiply it by the first derivative. So now that's me mx, and then finally we'll multiply b by our original guess solution, e to the mx, and all of that equals 0. So now what we can do, because we have this e to the mx in all of our terms, we can eliminate that by effectively dividing both sides by e to the mx. And we get the following equation, m squared plus am plus b equals 0. And so now what we have here is a quadratic equation, okay? And we can solve that in a variety of ways. So we refer to this as the auxiliary equation. And depending on the value of these constants, or what type, if I even had a first derivative, we might have to use the quadratic equation to solve it, or solve it if it ends up being a perfect square. So we have a variety of different options for solving this thing, okay? And now when we solve it, there's 3 different possibilities, right? A possibility with real roots, a possibility with imaginary roots, and a possibility with complex roots. So I'm going to go over here and look at our recipe that gives us a guide and tells us what's going on with this thing. And so if we were to get real roots, sorry, I'm just navigating over to my notes here. So if we end up with real roots, right, we solve the quadratic equation, then we might say m is plus or minus a, right? We get 2 roots because it's a quadratic. And so then plugging that back into our original guess solution, we would say y1 equals e to the ax. And of course, because it could be a plus or minus due to it being a quadratic, we could say y2 is equal to e to the negative ax. And now what we need to do is impose a linear combination of these two solutions. So we'll say our total solution for y is some linear combination e to the ax plus e to the minus ax, but we also have to impose some constants that go in front of each of these terms because we don't know what weight each term will carry. So all the same, this will be our general solution if we are to have real roots. Okay. So now, as you might imagine, we could have a situation in which we have imaginary roots. And in that case, our m would be plus or minus I times b. I'm just using the letter b for a different constant. And now we would follow the same procedure. We would say y1 equals e to the ibx, y2 equals e to the negative ibx, and then now we'll make some linear combination with these weighting coefficients out in front. E to the negative ibx. And then now this becomes, that's an imaginary number I right there, this becomes our general solution if we have imaginary roots. And of course, finally, we could have a situation in which we have complex roots. And that would go as m equals a plus or minus ib. And once again, we're going to follow the same procedure. We're going to say one of our solutions is e to the a plus ib all times x. And our second solution is the negative root. Or really, I should say the complex conjugate, right? It's not a negative root, it's a complex conjugate root. A minus ib all quantity times x. And then, of course, we'll make a linear combination with weighting coefficients of those two solutions. So a plus I times b all times x plus c2e to the a minus ib all times x. And once again, here is our general solution. And through our process of normalization, which we discussed previously, we can find the values of these constants to normalize these wave functions to 1. Okay, so let's keep going with this. Let's apply this method and solve our one-dimensional time-independent translational motion Schrodinger equation. And to make this a little bit easier for our opening bit here, we are going to assume that the potential energy is 0. And now our goal is to follow this Ansatz method. And so I'm going to give us 4 steps to follow to make this easy for us to remember. Step 1, cry. Step 2, pray. Step 3, guess. Step 4, solve. Cry, pray, guess, solve. That is how we're going to solve the Schrodinger equation. Okay, so do the crying, do the praying. Let's get it going. So I'm going to do some algebra to rearrange this into our standard form. So first, let's go ahead and write down the equation without that potential energy term, right? Because for now, we're saying potential energy is 0. I'm going to do some algebra here to get this into that standard reduced form by pushing all of the constants over to one side. And now that equals negative 2me over h bar squared all times psi of x. And I'm going to add that over to the other side now to get it into that reduced form. Plus 2me over h bar squared psi of x all equals 0. And now we'll make our standard guess. And because we have this second order differential equation, our standard guess for psi is going to go e to the, I'm going to impose another constant because I've just used way too many, and I'm going to say kx. And then now that means my first derivative of psi of x is ke kx. And then now my second derivative of psi of x is k squared ekx. And so you now notice here in our standard form, we didn't actually need the first derivative. We did need it to take the second derivative, but this is kind of what I was alluding to earlier, that we might not have like a full quadratic form like what we saw in the example. So now let's plug in our guess solutions back in. So second derivative of psi of x is k squared ekx plus 2me all over h bar squared times psi, which we guessed to be ekx, all equals 0. So now we can drop the ekx, right, just like we did before, and that becomes k squared plus 2me all over h bar squared equals 0. And now, as you can see here, we don't need the quadratic equation to solve this. It's going to go simply k squared equals negative 2me over h bar squared. And aha, we're going to have a situation where we're going to have to invoke some imaginary numbers. Okay, so I will now say that all of this equals k equals I to the square root of 2me over h bar squared. Beautiful. And I'm going to call this k prime right here because we already came up with this collection of constants for the letter k, right? So we'll go on and say that k prime equals I k. And as you can see, that is an imaginary roots situation. And so I'm going to skip straight to the next slide where I've got the solution already written out. As you can see now, we're going to have this linear combination of eikx and e minus ikx. And instead of using C1 and C2 like was done around here, I'm just going to use the letters A and B. So we can see that our Schrodinger equation is this linear combination of exponentials. But if you recall earlier, we came up with the cosine function. So how did we get that? Well, if you recall our Euler relationships, right? A cosine is technically a linear combination of eix and e minus ix. So that's why we just replaced this whole thing with cosine. So as it turns out, a sine is also a linear combination of these quantities. So what is standard to do is rewrite this in terms of both sines and cosines. So what that means now is we're going to write that psi of x equals the following. I'm going to say A, and now I'm going to invoke that combination right here that I got, okay? And I'm going to drop the 1/2 just for ease, because as we'll see, this is all going to get collected into a whole mess of constants. So this ends up becoming, let's see here, eikx becomes the following, right? So do the algebra, and this is what we get. And really, that's why the 1/2 got dropped out. Apologies for that confusion. So cosine x plus I sine x, okay? Now plus b times e to the minus ix, which is going to be cosine of x minus I sine of x. And now our process is to combine the like terms with the cosines and the sines. So let's go ahead and do that. So as you can see, I can collect like terms with the a and the b times cosine. And I realize I dropped writing the k. Apologies there. Let me squeeze those k's in. Right? They were not present in the general solution, but we need them in our specific Schrodinger equation solution, kx, there we go. So now that's cosine of kx plus, and then now I can combine the sines, and we notice that both of those have imaginary number I, and that becomes a minus b times sine kx. And now our standard procedure here at this point, because we recognize a and b are constants, And of course, I is an imaginary number. We're just going to lump all of these into some new constant that I'm going to call C times cosine kx plus, and I'm going to lump this whole thing, IA minus B, into this other constant, D times sine kx. And now this is another way we could write our solution as this linear combination of cosines and sines. And we also note here now, because there's an I in there, we can see using the square modulus is really going to be necessary because that's going to help us get rid of that I from the square modulus result. Okay, that was a lot. We're going to practice this in our live lecture.